One more example for class 10. This is example 311 of the textbook. I think it's a pretty interesting one. I filled up the page with a lot of this information for this one. For one thing I didn't like is they called this thing water, but it's actually steam. But yeah, I kind of thought of it as being liquid because they said water here at the beginning. But let's just take a look. The piston cylinder setup shown in this figure contains 0.1 kilograms of water at 1000 kPa, 500 degrees Celsius. The water is now cooled with a constant force on the piston until it reaches half of the initial volume. After this, it cools to 25 degrees Celsius while the piston is against the stops. Find the final water pressure and the work and heat transfer in the overall process and show the process in a PV diagram, which obviously they've already done for you because I have it right here in front of us. But if they didn't show it to us, we have to play that game where we're reading between the lines to try to understand what's actually taking place. Man, that's the hardest part of this whole course. But of course, it's really the hardest part of most engineering courses, or maybe it is the hard part of being an engineer, right? It's just trying to understand what's really taking place and what really needs to be done to solve whatever problem that's put in front of you. So one of the keys here is it has this constant force. That constant force, very much like some of the problems where the piston had a weight onto it, because the force is constant and the area is constant, the pressure is going to be constant right up into the point where it's on these stops. Then it's going to be on these stops and it can't move, so it's going to be a constant volume process from there on. So you can tell that from the PV diagram. And as we go look at this, we're going to start right here from the state that we were given, 1000 kPa, 500 degrees Celsius. We're going to find that superheated, so it's outside the vapor dome. But as soon as we keep on this constant pressure and we get to this location here, which is going to be like at 25 degrees Celsius or something along those lines, we're going to now start having a constant volume process. So that's like the big picture, and you got to kind of try to imagine it from what you know already. So let's go to the tables and first start out with let's pretend we already know that it's going to be superheated. Right, so we'll go to table B.1.3, and at P is equal to 1000 kPa, and T is equal to 500. We can get all the parameters, all the parameters we need. You're gonna start punching. You getting punchy? No. We're fine. All right, so here's saturated water vapor, and this looks like what we needed right there. Boom. We need this, but we need on the previous page because this goes to 700. So on the previous page, there you go. It was already highlighted. I wonder why. Because I did this problem already. So we're going to write that down. We're going to write down the specific volume of, I'm going to call it state 1. Of 0.35411 cubic meters per kilogram. And then U, call that U1, of 3,124.34 kilojoules per kilogram. Let's get rid of it so we don't have to live with it forever. All right, so and I'm just looking at my paper here and going, why did I do that for? Okay, so state 2, it reaches half of its initial volume. All right, so here's state 1. State 1, I like to circle states. I wish I put this up here at the top. Let's pretend I did. Let me go to state 2. I'm trying to conserve paper because this is, I ran out of paper before. State 2, V2 is equal to 1/2 V1. right? So that's going to be like when the piston is like right into that place right there. By the way, I should have drawn anyway, so V2 is equal to 1/2 0.35411 or 0.17706 kilogram. So what we want to try to do is, oh, and by the way, P2 is equal to P1. This is a constant pressure, is isobaric, right? Because of the constant force. So that's going to be 1,000 kilopascals. So all right, so this right here starts at, I call it state 3, right? I'm sorry, the book called it, I already have it written down this way, so I'm not going to change it, but I called this 1, this 2, and this 3. But what are you going to do? It's whatever you call it. So let's go to and see where this is in the saturated tables. So this is table B point. Let's go to the indexed ones that are indexed by the saturated table is indexed by pressure right here, right? And this is the enthalpy page. So let's go to this page, and we're at 1,000, right? Take a look here, and you can see, yes, here's the gas. That's 0.19. We are at 0.177. So we're in between this liquid and this gas. So we can find out what the quality is right now. So I'm going to write down this information, right? So here at P is equal to 1,000 kilopascals. T sat. Sometimes we're going to need it, sometimes we might not, but good information to write down. And then we're going to write down the VF is equal to 0.001127 cubic meters per kilogram. And the VFG is going to be 0.19332 cubic meters per kilogram. And UF is 761.67 kilojoules per kilogram. And UFG is 1821.97 kilojoules per kilogram. All right, so let's get the quality. I'll get the camera to come back on. Hello, 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 come back on. So we go, V is equal to, let's move this up here. V is equal to VF plus X VFG. So that's going to be 0.17706 from there. It's going to be equal to 0.001127 plus X times 0.19332. And so we will get, for an X, we will get 0.9100 or 91%. So then we can get for U, UF plus X times UFG, and that's 761.67 plus 0.9100 times 1821.97. And where'd you go, Joe? 2419.7 kilojoules per kilogram. I'm not 100% sure I needed that, tell you the truth. Maybe. Anyway, for the next part of it, we need to go down to 2. So it's going to go from here downward, straight down. So it's going to keep constant volume, right? So state 3. And state 3, it's going to be T3 is equal to 25 degrees Celsius. So they're going to cool it down. So it went to right around 180 degrees, and now we're going to be at a constant volume. And so it's just going to keep on dipping down. So we're going to go to this and go to table B.1.1, right? At that temperature condition. Is the right one? I think so. 25 degrees. 25 degrees. Here you go. At 25 degrees, for one thing, the pressure, Psat, is 3.169. It's very small. It's getting near perfect vacuum. If you take a look at the volume, it's going to be a very, very, very small volume because of the VF. You can take a look. So it's going to be very I think I'm saying it the right way. The quality is going to go way down. Put it that way. The VF is 0.001003, which isn't really hardly ever changes all that much. And I'm so tired. I just wrote pounds mass underneath it. It's not right. Kilograms, and that's the F, and then the VFG is a large 43.358 per kilogram. And we're going to want to know the U's too, so I'm going to write that down. UF is going to be 104.86, and UFG is going to be 2304.90. It was a really exciting video when I'm writing things down while you stare at the thing. And these are kilojoules per kilogram. All right, so one of the reasons why we go through this, one of the mindsets, in this particular step, is we need the quality from this so we can use the quality to find out what this end result is going to be. So we use the information that we have. What we know is that the V. Let's see, I'm double checking thing that I want to say here. We're still going to maintain this same value right here, 0.17706, right? But now we're going to have a new quality because we're going to go 0.001003 plus X times 43.3583. And our new X for this is going to be very small. It's 0.00, so it's less than 1%. It's 0.4%. That's not much. But what we're able to get from that, U3, is this value. Multiply it by that 2304. And what are we left with? Looks like 114.22 kilojoules per kilogram. All right. So we're getting really close to finishing up here. we did find what this right here is actually the answer to this first part right here. Find the final water pressure. And they're saying water, but it's a mix. It's not much of a mix. It's very much closer to water than it is anything else, right? We're still underneath the vapor dome, but we definitely have gone over to the left of the vapor dome. Because remember, like it would be, if it touches over here, that has a quality of 0. If it touches over here, that's a quality of 1. We're usually talking about steam, right? So this is not as low, very low quality, if you will, of steam. See where I'm at. Okay, so I want to get the work now. So the work is only going to be that part that goes in a constant pressure that goes from here to here, right? It's going to be the area underneath there. You can see that nothing happens between what I dubbed 2 and 3, what they called 1B and 2, right there. So this, call it 1 to 2 or 1 to 3. I guess 1 to 3, right? Integral from 1 to 3 of P dV. So this is going to be the pressure, because it's a constant pressure process at that spot. So it's 1 million newtons per meter squared. And now here's an important thing, and I should have written out the equation, but I'm very tired. It's late at night. So well, it's not late. It's like 11:33, but it's late. See, it says right down there, right? Right there, it says 11:30. Let's see. Shut up. Haven't used that in a while. What am I writing? Oh yeah, okay. So this is gonna be V2 minus V1. So V2 was this 0.7706. We need a 1 in there. Get that right? Minus the initial one way the hell up at the bottom top. That was 0.35411. 35411. And what we end up getting is a, I'm going to go ahead and divide by 1,000 because I'm lazy, but because I multiply by 1,000, it'll come out, it'll work out. No pun intended. We get a negative 17.71 kilojoules. I would have gotten 17,710 with these values right here. Negative. Why is it negative? Because work is being done onto the system. We have work coming in, W in, if you will, because of this force, right? So that's our convention, is it for it to be negative. And then Q 1 to 3. Well, we should really write this right down. I'm tired. U2 minus U1 equals Q, or U3 minus 1 is 1 to 3 minus work 1 to 3. You want to be careful. Sometimes you do need to break it down into these stages of 1 to 2 and then 2 to 3. Just be aware of that. This time you don't have to. So anyway, Q1 to 3 is going to be equal to U3 minus U1 and then plus work 1, 2, 3. We need the mass. Did we ever find the mass? We were told the mass, 1 kilogram. So we go, or 0.1 kilogram. And then the U3 was the one we just found. 114.22. And then minus the initial U, which was 3124. Wow. 3,124.34. Boom. And then plus, this is crazy, a minus 17.71. You'll notice that's a negative number as well, right? This is bigger than that. That's because we're removing heat. our normal convention is to have a positive heat is coming into, but we are going to remove Q from this. Therefore, we're going to have a negative value from our convention. So 1 to 3 is going to be a negative 318.7 kilojoules. I didn't do a good job with keeping my paper in place, but it's already 20 minutes into this video, so I didn't want to make it any worse. Good night, and we will start on the next subject, which will be chapter 11 very soon. Good night.